Welcome to Brain Vision.
All right, this problem takes a kind of clever trick. It has a somewhat complicated setup, so we'll try to walk through this slowly here. So the problem's over here on the left. So we have a square of current with current I flowing through it clockwise like this. And we want to find what the magnetic field due to this loop is over at point P. So the square has sides length d, and then point P is a distance, an additional distance d, away from the edge of the loop over here. Now the problem tells us to use the results from the previous problem, problem 41, in order to do this. So in that we found two things. One is that if we have some point P that is parallel with a line of current, so this is some wire carrying current here, and then parallel along that we have point P, the magnetic field is going to be zero. And that's not too hard to believe because the angle between these two lines is zero, so the cross product is going to be zero. So if you did the Biot-Savart law, it would have to be zero. So it tells us that, and then additionally we found that if instead point P is raised above the wire, so rather than being over here is up like this at a right angle from the edge of the wire, then we find the magnetic field as this whole expression. So mu naught I over 4 pi, and then divided by y times y squared plus d squared to the 1/2, and then another d on top, and of course in the k-hat direction. So the relevant things being d, the length of the wire, and then y, the height above the wire or away from the wire that point P is. So if we look at our loop here, I've labeled all the wires 1, 2, 3, and 4, and actually this result applies to all of these sides except the last one. So wire 1 is exactly this first case as described here. So we know the magnetic field from that would be 0. And then wire 2 and wire 3, we can see is actually like this case. It just rotated 90 degrees. So if we rotated this whole thing by 90 degrees, then it's actually describing the same case. So it's just rather than point P being a distance y away here, it's a distance of 2d for wire 2, or just a distance of d for wire 3. So the only one that doesn't work is wire 4, because we only have a result for if the wire extends all the way out to be directly below point P. So what we'll actually do is say, well, let's just extend wire 4. So let's pretend wire 4 actually goes this whole distance and still has the same current going through. So now we'd be able to apply this result to solve for it there. But we can't just change the problem. So in order to make this still work, what we'll do is we'll add another wire. So I'll draw this a little bit below, but this wire is directly on top of the previous wire. And so this fifth wire, in order to cancel this out, we'll have a current going the opposite direction. And so definitely if we're just thinking about these two segments of wire here, so half of 4 and then wire 5, if they're directly on top of each other with opposite currents, the net current 0, it's making no magnetic field. And so this can't have changed the problem at all. But just setting it up like this will make it easier to solve using the results we already have. So to find the total magnetic field then, we're just going to say that's equal to the field from all of these different segments. So we have B1 plus B2, B3, B4, and B5. So B1 right away we know is just 0, since that's the one that's parallel along with point P here. So now we just need to do points 2, 3, 4, and 5. And now as we've set it up, it's really going to just be applying this equation and carefully substituting in for y, so it's perpendicular distance away from point P, and then what d is the length of the wire here. And then we'll be using the right-hand rule just to find if it's positive or negative. So we know all of these terms are going to have a mu naught I over 4 pi in them, since they all have the same magnitude of current. So I'm just going to start by writing that, and we'll just have that factored out so we don't have to write it a bunch of times. So B1 we know 0. Now B2, so this has a length of d, so d equals d in this expression. And then it's a distance of 2d, away from point P. So y here is 2d. So we have d over d, and then y is 2d, so 2d quantity squared is 4d squared, and then we have another plus d squared to the 1/2. And then if we are careful with our signs, check the right-hand rule, this should have a minus sign. So this is the B2 term, and we're just doing the exact same things for all the others. So B3, now we have current going the opposite direction, so if this one was minus, this one's probably going to be a plus. And now y is equal to d, and d is equal to d. So this one will just have d over d times d squared plus d squared to the 1/2. And so the other ones we're doing just the same. Now we have wire 4, which remember we've extended along this whole distance. So its y is just d, this height here, but its d in this equation is now 2d. So we should have minus 2d over d times d squared plus 4d squared to the 1/2. So this was the y times y squared, and then this is the d squared term. So I'm following the exact form of this, so you can kind of check that the terms line up more easily. And then our last one, wire 5. So again, careful with our signs. This one will be a plus, and that is a distance d away, and then has a wire length of d. So this one is just all d's. And we have this whole big mess. And so we can see we're always going to have a d over a d, so we can cancel all of those out. And then we're going to have some d squareds in the denominator to the 1/2, so we'll definitely be able to pull out another d. So this will become mu naught I over 4 pi d. And now all we're going to be left with is just 1 over and then the square root of the number of d's in the parentheses. So this will be -1 over root 5, and then we'll have plus 1 over root 2, and then minus 2 over root 5, and then plus 1 over root 2. And, oh, whoops, I think this should have been a 2D, since so for wire 2, our distance away from point P was 2D. So yeah, that should have been a 2. So we get a 2 there as well. And now if we add up all these fractions and kind of make it a little more pretty, we should get, well, we still have this mu naught I over 4 pi d. And then we'll end with times root 2 minus root 5 over 2. And this is all in the k-hat direction. So reduced down to a pretty clean expression, and there we go.